Okay, now we're heading into Unit 9. I know it says Chapter 16. And what we're talking about is we're switching gears quite a bit and talking about electric charge, how it behaves and that kind of thing. So what's weird about electric charge is if you rub a balloon or a comb or whatever through your hair or on a sweater, you can use it to pick up little bits of paper and whatever. And that force seems pretty strange to us. This invisible force that can reach across the space and grab things and pick them up. But it's really no more strange than gravity, which can, if you jump up, reach up to you and pull you down. But it definitely seems a lot more strange to us because it's not seen as often. And what's doing that is the fact that there's a buildup of electric charge, and it's always, well, it's not always going to be, let's just leave it at that. Either positive or negative charge. And if there's a buildup of electrons, if there's extra electrons, the electrons aren't moving, they're not in current electricity like in your wires or your house. They're called static electricity because they're not moving, so static means not moving. So the study of stationary charges is called electrostatics. And that's really what we're doing in this unit is electrostatics. Okay, so which of these forces is generally stronger in everyday life? Well, we would definitely say gravity is. Now, that doesn't mean that gravity is a stronger force. It just means that that's what we perceive in everyday life. And the reason for that is there's usually not a buildup of electrical charge. It usually distributes itself. Okay, but I could take a little comb or a little rubber balloon and pick up a piece of paper off my desk with that. And basically, I'd be canceling out the gravity from the entire Earth, the entire massive Earth, okay, with just a little comb. Okay? And that's because the electrostatic force is actually a much stronger force. So if I had 2 kilograms of electrons separated by a distance of 1 meter, the force of attraction due to gravity would be this small, tiny fraction of a Newton, barely anything. However, the electrostatic force between them due to their charge would be this many newtons. And obviously we'd never be able to even get a kilogram of electrons close to another kilogram of electrons because of the massive amount of force that we're talking about. Now, when we did mechanics, one of the main ideas was mass, and we never really said what mass is. We just basically said this is what mass does. Okay, when you put two objects that have mass in the same space, it can be the same universe for that matter, they exert a force on each other, and we call that force gravity. Okay, it's an attractive force. When you try to accelerate an object with mass, it will resist that, and that property of mass that does that we call inertia. Okay? If you have mass that's moving, okay, well, that object possesses a property called momentum. If an object is moving or elevated or any number of other possibilities, that mass can also possess energy. Okay, we never really said what it was though, and that's because we really don't know what it is. We know that through experiment that gravitational mass and inertial mass appear to be the same thing, okay, but there's no necessary reason why gravitational mass and inertial mass have to be the exact same thing, but they've tested it down to I don't know how many decimal places and found that it so far it appears to be the same thing. Now, what the fundamental idea is in electrostatics is charge, and again, we're not really going to say what charge is. I don't know, in my mind, charge is this magical property that's imbued upon certain particles. But we're not really going to say what it is. We're just going to basically say what it does, okay, how it behaves. There's two types of charges. There's positive charge and negative charge. Like charges repel each other, so two positives repel and two negatives repel. So like charges repel. Opposite charges attract. Okay. All the charge in the universe comes from just two particles. All the negative charge in the universe comes from electrons, and all positive charge in the universe comes from protons. But if I have well, you're made up of both of those charges as well as neutrons. Typically, you're neutral. How is it that an atom can become neutral if it has protons and electrons and neutrons? Okay, if it's got protons which are positive and electrons which are negative, how can they be neutral? Think back to chemistry. Then basically you just have to have the same number of each, and that charge cancels out. Okay. Now the nucleus is this tiny fraction of the volume of an atom. I mean, it's just a speck in a speck anyway. However, it's 99.9% of the mass. Electrons do not have very much mass at all, and they're kind of, I don't know, depending on what model the electron you're using, sort of in this cloud around the nucleus. So the nucleus contains protons and neutrons. Well, what do the neutrons do? Well, these protons are trying to get away from each other because they're positive, and the neutrons are the glue that holds the nucleus together. It keeps all those protons from flying off. Okay. Now, if I've got a neutral atom here, how does it become a positive ion? How does it become a positive ion? Okay. Well, it can gain a proton. Okay. Or the other way and that's not really what happens from chemistry. We should know better. How an atom typically becomes a positively charged ion is by losing an electron. Okay, and remember from chemistry we call these cations. Okay, so if you've got more protons than electrons, you are electropositive. Okay, and how does an atom become a negative electron or a negative ion? Okay. Well, it gains an electron. So the electrons are the only things that move around. Okay, the protons are stuck in the nucleus. Okay, if we start moving the protons around, that's a nuclear reaction. Okay, that doesn't happen when you rub your comb on your hair. Okay, you do not start setting up nuclear reactions. It's the electrons that are moving around. Okay, and that's called an anion. Back when I was an engineer, I was working with some guy who called them cations and anions. I thought that was funny. I mean, there's no reason that they couldn't be called that. Okay, so let's look at this. So what are the missing charges here? Take a moment and pause this and see if you can figure out what's what. Okay, so pause it and figure out. It gives you that B is negative. Okay, all right. So if B is negative, that means that A has to be positive, okay, because they're attracting. And if B is negative, C has to be negative because they're repelling. All right. Let's look at this one. So B is negative, so that means that A has to be positive again, okay. And if A is positive, then C has to be positive because they're repelling. Okay. And that is the answers to that. But I just went over that anyway. Okay. Now, the charge on a proton is exactly equal to the charge on an electron. Okay, it's just one is negative and the other is positive. So normally in chemistry, we say something has a 1 minus or a 1 plus charge, and that means it's gained or lost exactly 1 electron. Okay. The charge on an electron cannot be split. There cannot be anything smaller than the charge on an electron. So if I tried, I would not be successful. Okay. Any charge that's on an object is just a multiple of the charge on an electron. Okay, but you can have more than one electron charge on an object, but it's got to be in the multiple of the charge on an electron. Conservation of charge. Charge cannot be created or destroyed, but it can be moved from one object to another. That sounds pretty familiar. That sounds like conservation of energy, where energy cannot be created or destroyed. It can just be transferred from one form to another. And this idea is really simple. When we rub two objects together, some objects typically are very good at stealing electrons from other objects. Plastics and rubbers and things like that tend to be really good at stealing electrons. Other objects don't tend to be very good at holding on to their electrons, like hair, glass, skin, things like that. So when I rub two objects together, so here we've got cloth and glass. Glass is typically pretty good at losing electrons. So when I rub these two together, okay, the electrons are going to get stolen by one object in this case. Okay. Now right now these objects start out as neutral. And why do they start out as neutral? Right, because they have the same number of protons and electrons, so they're net neutral. Okay. So when I rub them together, okay, electrons are going to move from one object to another. The electrons don't just spontaneously appear. Okay, I don't create electrons by rubbing two things together. They're just transferred from one object to another. Okay, so now afterwards, this cloth, which now has two extra electrons, is a 2- charge. Okay, and the glass, which has 2 extra protons, has a 2+ charge. So and notice that my charge is conserved. I started out with 0 charge. Afterwards, I ended up with a 2- and a 2+. My total charge is back to 0. So it all adds up. Now this time, if I rub the cloth with a piece of rubber, okay, something different will happen. It's going to explode. No, the rubber is an electron stealer. Okay, so this time the cloth is going to end up positive. Okay, and the rubber is going to end up negative, and they ended up with a 2 positive charge here and a 2 negative charge here. Okay, so I already kind of went over this. So initially I started out with a neutral object, so 0 and 0. After I rubbed them together, the cloth transferred 2 of its electrons to the rubber. So the cloth lost 2 electrons, so it ends up with the 2+. The rubber gained 2 electrons and ended up with a 2-. And when I add up my charges at the end of the day, I end up with 0 again, because charge was just transferred from one object to another. Okay. There's something called the triboelectric series, which is kind of interesting. So on this one, the upper side, on the upper top side, you've got objects that are pretty good at losing electrons. Okay, and we've got human hands that appear to be the best at that. Asbestos, rabbit fur, glass, human hair, nylon. I think a lot of carpets made out of nylon, and wool, fur, etc., things like that. Down here you've got the electron stealers, which tend to end up negative. So you've got I don't even see rubber down here. Different types of plastics and things like that. And so when you rub your rubber, which is going to be in here somewhere down in the electron stealers, it's going to take electrons from this carpet, which, let's say it's nylon carpet, and you're gonna gain electrons. So let's see John Travoltage here. So here's John Travolta, and here's rubbing his foot on the carpet. Oh man! And here he's gonna touch the doorknob. Ouch! Ouch! He's building up charge. Ouch! Ouch! So anyway, he was stealing electrons from the carpet, and the carpet became positively charged, and he became negatively charged, and then that's what causes that static discharge. It's the friction between the feet and the carpet. Okay, so recap: how does an object become negatively charged? It gains electrons. How does an object become positively charged? It loses electrons, and that's pretty much that. So now Ben Franklin did some work with this back in the day, a long time ago, and he was the one that discovered that there were two different charges. He found that if he rubbed glass rods with some fabric, that they would repel each other, and he didn't know that they both had the same charge, or the same positive charge. But what's interesting is when he rubbed, I think he used amber, but we're going to say rubber. When he rubbed two sticks of rubber with a cloth, they repelled each other. But when he held the glass to the rubber, it attracted. Okay, so he uses this logic to come up with the idea of saying, all right, there's two different charges. Okay, and I'm sure he repeated this with any number of objects that he had around the place. So how did one become positive and one become negative? Basically, he had to call them something. So he just decided, I dubbed the charge on positive rod, call you positive, and I call you negative on the rubber. He just basically had to come up with something so positive and negative seemed as good as anything. Now remember, the smallest charge that an object can have is 1 electron. Okay, so a 1 minus charge. So charge is quantified or quantized. That's what quantized means, is it comes in chunks. Okay, the charge on an electron, this would be a number that I would have handy, or program it into your calculator, equal to the letter E. 1.60 times 10 to the minus 19th coulombs. Coulombs is what we measure electrical charge in. Okay, any charge on any object is some whole number multiple of this number. Now it's really, really small, so it's not like an object ends up with big differences. Okay, you can't really tell the addition of 1 electron on a normal size object. So it's not like we notice that there are chunks of charge that are being charged. So anyway, keep that number in mind. On your equation sheet, that is listed under constants and conversion factors. So E, the electron charge magnitude, is equal to 1.60 times 10 to the minus 19th coulombs. Okay, so that's where you can find it. So here I've got a video. This is a video, an experiment done by Robert Millikan to determine the charge to mass ratio of a electron. So he's credited with discovering the charge on an electron, and it always amazes me the ingenuity of these early experimenters, with what they had. So anyway, it's kind of interesting, I think.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of...
I misspoke. He didn't calculate the charge to mass ratio. He calculated the actual charge on the electron. So I made a mistake there.
Charges produced by the X-rays attached to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron. In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge.
That started again. I believe, let's see if there's anything else I wanted to cover today. We are almost done. Okay. All right. So, how many electrons would I need to have a full Coulomb of charge? Well, the E is equal to the 1.60 times 10 to the negative 19 coulombs per electron. So if I wanted to know electrons per coulomb, I would take the inverse of that. So it would be 1 divided by 1.60 times 10 to the minus 19. And you'd end up with a pretty good sized number. It takes a whole lot of electrons to make a charge. So you're not gonna see walking down the street an object that's got a Coulomb of charge, because that's a whole lot of charge. It's just it would tend to equalize out before it builds up that much. So anyway, that is it for the day. Thank you for listening, and have a good day.